Greetings, was asked to do a video on problem 6U try, the use of a common ratio and identifying exponential data. So given the data table, explain why the data can be best modeled by an exponential function. Use the idea of a common ratio in your response. Okay, so one thing you could do, and I'll actually encourage you to do this, is to go ahead and enter that data into L1 and L2 and do a scatter plot of it and see that it looks like it's forming an exponential set of data. So remember from our work previously with linear functions in regression that we can actually do scatter plots to identify the shape of a model. But that said, let's take a look at what they mean by the common ratio. So the way to think about the common ratio is that you take a look at two successive values from your y list or from your f of x list, and you form the ratio of those two. And if that ratio remains constant across all successive values in your y list or your f of x list, then that is a very good indication that your data is being modeled best by an exponential model. So in this case, our common ratio, which in the case of our model, the way we're working, that's going to be b. In other words, we're using b to represent our common ratio between terms. That's going to be what? 12 divided by 15 if we take a look at the first ones. So going to get our calculator here. Let's go grab our calculator real quick. So if we take 12 divided by 15, and we can even ask it to return that as a reduced fraction for us, and we get back 4/5, or you can take 4 divided by 5 if you'd like and get back a common ratio of 0.8. Either way works, all right? So what we see is that we get back here either a fraction of 4/5, which is equal to 0.8. All right, so I'm going to leave it to you. I'm not going to go through showing you this on every one of them, but you need to take the 9, well, I'll do one more just to show what I'm talking about. Take the next successive and see if those turn out to be the same value also. In other words, take 9.6, divide that by 12, and does that again come out to be equal to 0.8? In other words, do we get the same common ratio for each pair of successive terms in the y list? So 9.6 divided by 12, and yay team, we get back 0.8 again, okay? And if you keep doing that for every successive pair, you're going to get back 0.8, okay? So your response to part A here is it appears to be a exponential function. I'll let you finish the sentence. I'm just going to start it for you here. To be exponential since common ratio is 0.8. And the main thing there, probably one of the things you should maybe be a little more explicit about is that that ratio remains consistent across all successive pairs in the y column, okay? So you add that verbiage in here. I'll let you put that in. Okay, part B. Determine the exponential function f of x equals a b to the x that fits these data. Start by identifying the values of a and b, and then write your final result. Okay, so a is the initial condition, okay? So a is always going to be equal to f of 0. So f of 0 will be equal to a, always. That's the initial part. And if you think about that in terms of the model here, let's come off to the side for you just a moment. The model is f of x is equal to a times b to the x power. Well, f of 0 is going to be a times b to the 0. And we know anything raised to the 0 power is a 1. So that's going to be f of 0 is equal to a times 1, because that's what b to the 0 is, which is just a, right? So f of 0 is equal to a. All right, so we can come over here and just read that from our table. We see f of 0 is equal to 15. So in our particular case, that means the a value will be equal to 15. Now what about b? Well, we just saw that back in part A, that b is equal to the common ratio. So the common ratio in our case is 0.8. So that tells us gloriously that f of x is equal to 15 times 0.8 raised to the x power. Cool. All right, so now we've got our model. So now that we know what our model is, they want us to determine a few values here. So they want us to, first off, tell them what f of 10 is equal to. So f of 10 is going to be, well, we plug that into our function here. So that's 15 times 0.8 raised to the 10th power. So let's go get our calculator out. And let's go ahead and do that. So we're going to take 15.8 raised to the 10th power, okay? And we get back, in this case, that's equal to, and they say round to the nearest hundredth, so let's go back and take a look at our screen again. So that's going to be what? 1.61. All right, now in part D, they give us a heads up. They say, oh, it's going to go into scientific notation here, so be warned that that's what's going to happen. So they want you to write it both as a decimal and in scientific notation. So we're going to have to do a little review of what scientific notation is. But let's go get our number first to help us with that. So f of 50 is going to be equal to 15 times 0.8 to the 50th power. Okay, so let's go get the calculator up here. So that's going to be 15 times 0.8 raised to the 50th. And what we notice is this crazy notation just came back out from the calculator. And it's 2.140871539E. Very important to see that E there, -4, okay? So what does that mean? All right, what that means is, I'm just going to go take it out 3 places on what's presented there. That's going to be plenty. So that would be what, 2.141? So this is going to be approximately 2.141 E. Let's go back here for just a moment. What was that? It was -4, right? Okay, so the thing to recognize or to recall, if you've worked with these calculators in scientific notation before, is that what that E means, when you see that E, that's equal to times 10, and then there's going to be the number that comes after. It's going to go up here in the exponential place. So for example, E -4, what that's equal to is that's times 10 to the -4th. In other words, that replaces your standard handwritten scientific notation. So if we come back here, I can rewrite this as 2.141 times 10 to the -4th. Okay, so that would be the scientific notation version of the answer, but they want us also to write it as a decimal. So recalling what that times 10 to the -4th means is that another way of thinking about that is that's 1 over 10 to the 4th power, because that's what the negative exponent means. Well, so that means what? That's 1 over 1, 2, 3, 4, or 1/10,000th. And notice that what that does is that takes the decimal point, which currently resides here and here at this point, and moves it 1, 2, 3, 4 places to the left. So this number is actually 0.0001, okay, moving the decimal point over 4 places. So the same thing here is going to happen. If I want to get this out of scientific notation, this means I need to move my decimal point 1, 2, 3, 4 places to the left. So this is going to be 0.0002 as a decimal. Hopefully that made sense. If it doesn't, please don't be shy about posting me more questions in the Q&A form, and I'll do whatever I can to make it make more sense. But in the meantime, let's just do a quick check of what I said at the start of this. In other words, let's take that data and let's plug that into our calculator. And let's show that this data fits quite nicely to an exponential model, okay? So I've already gone through the push-up of putting the data into L1 and L2 and done a scatter plot. Just to show you that real quick. Just went into Stat, went to Edit, put the data in L1 and L2. Then I went into Stat Plot, just like we did back in the last chapter. Turned Plot 1 on, made it a scatter plot, L1, L2, did a zoom and a 9, and bada bing, bada boom, there's my scatter plot. Okay, so let's go back into the y equals menu and let's put our model in here just to show that indeed it does graph right over the top of it. So our model is what? It's 15 times 0.8 raised to the x. Okay, let's push graph. Yeah, looky, looky, it graphs right over the top of our data. Isn't that nice? Okay, so please take the time to make sure all this makes sense, and if you need any extra help, please do not be shy about asking for it.